Quantum tunneling. Can music be faster than light? Nothing can be faster than light. For sure, you have heard this phrase sometimes in your life. But is it actually true? Well, yes and no. Let's have a deeper look into that question. To understand where the above axiom comes from, we have to go back to Einstein's special relativity theory, which says that if you take a mass and you accelerate it up to a relativistic speed, that means close to the speed of light c, its mass will grow exponentially during this acceleration process, like you see in this diagram. This means, of course, that nothing with mass can be accelerated to the speed of light, as you would need infinite energy to do so. But what about light? Light consists of small particles called photons that obviously propagate at the speed of light. After the Einstein equation, this means automatically that there can't be any measurable mass of the particle. But how on earth can you make a photon run faster than something without mass? Spoiler alert, you can't. But what about quantum tunneling? Well, to understand quantum tunneling, you could imagine a huge tube where the photons move from one end to the other. But when at some point you make the tube so small that a single photon cannot pass this tight spot anymore, you will still receive some photons on the other side of the tube. So why is that? Imagine a Newton cradle. When the first sphere touches the others, the impulse is nearly transmitted immediately through the whole cradle onto the last sphere, which then starts moving. Although this comparison is not quite accurate, it gives a pretty good idea of what happens during quantum tunneling. The photons bounce on some sort of impenetrable barrier and immediately immerse on the other side, although they physically could not get through this barrier. In the mid-1990s, German physicists Günther Nitz, Eichmann and Strasser managed to get Mozart's 40th Symphony tunneled through a waveguide at the Hewlett-Packard Laboratory. They measured 4.7 times the speed of light over the whole distance. So, how was that possible? As we know, speed is defined as distance per time. Let's say a particle moves at a speed of 1 foot per second. This means that in 3 seconds, it moves through a distance of 3 feet, obviously. When you tunnel that particle through a 2-foot distance, that means the particle disappears at the entrance of the tunnel and immediately reappears on the other side. You automatically measure a higher speed than before, as you just cut out the length of the tunnel itself. So you still have a 3 feet total distance, but actually, the particle only moves through 1 foot, as it never actually moved through the 2 feet tunnel. You will measure a speed of 3 feet 1 second equals 3 feet second. This means the longer you make the tunnel distance, the higher the measured speed will become. But as you might already have guessed, this has nothing to do with a photon reaching a higher speed than the speed of light at any time. It just means that, like in Newton's cradle, the photon bounces onto a barrier that it cannot pass. Then it somehow transforms into virtual particles, at least that is the current theory, and then, at the other side of the barrier, without any time delay, reappears and continues its journey as a photon that contains the same information like the original photon. So, no, you cannot get light to run faster than light, but as you see, you actually don't need to in order to get information transmitted with a higher-than-light speed. Another method of transmitting information with a speed greater than the speed of light is quantum entanglement, where two particles are entangled in a way that a change on one particle is reflected immediately by the other particle without any delay, and this, at least in theory, over great distances. This means you could place one entangled particle on the other side of the galaxy and then still have a real-time communication by manipulating this particle, as its counterpart on the other side of the galaxy will copy all changes in real time. But you still don't get a higher speed than the speed of light. You just sort of eliminate the distance. So, I hope that you found this video interesting, and please let me know in the comments what subject you would like to hear more from. Stay curious and keep exploring. If you want to help out the channel, please consider to like and subscribe, and also leave a comment, as this pushes the algorithm.